In the next 6 videos, starting from this one, I'll be talking about indicial or exponential equations. And in this particular video, the focus is on solving indicial equations by equating indices. So we'll be looking at different methods uh, by which we can solve exponential or what we know as indicial equations. So this is uh, the most basic approach when we come across indicial equations. We try to equate indices, right? So, of course, the learning outcome here is to be able to solve standard indicial equations quickly and confidently. So first off, what are indicial equations? What is an indicial equation? It is simply that equation where the unknown appears in the exponent or at the index. So we are used to having equations like, you have maybe you have 3x squared plus 5x minus 7 equals 0. This is a quadratic expression, for instance, or a polynomial equation. But what if you then have, say, 7 raised to power 3x squared plus 5x minus 7 equals something? Maybe it can be anything, maybe equals 49, then this becomes an indicial equation because the unknowns are, are the index level, not just the regular polynomials we know. So those are indicial. That's a good example of an indicial or exponential equation. So we have some examples like 3 raised to power 2x equals 3 raised to power x plus 4. We have 5 raised to power x squared minus 1 equals 5 raised to power 3x plus 2. The key idea here is that if two powers have the same base, we can equate their exponents under certain conditions. So once the bases are the same, like these two examples now, the base for the first one is 3. So it means you can simply equate 2x to x plus 4 and then solve that to get x to be equal to 4, I think. Then here you can since 5 is the base on both left and right hand sides, you can simply say x squared minus 1 is the same thing as 3x plus 2, and then you solve. So that's what an indicial equation looks like. So let's look at the color for indicial equations for solving them. So the color here is that if a is raised to power f of x, and that is equal to a raised to power g of x, because the base is the same on both sides, a is the base on both sides, then you can then compare the powers, the exponents, which is fx and gx. So in that case, we can say f of x is equal to g of x. We have based on these conditions, though. First of all, this rule works only if number one, the bases are identical. That is, this is a and this is a. But that's not enough. Number two, a is greater than 0. So if you have a to be 0 or negative, that won't work. So you need a to be greater than 0. Number three, a must not be equal to 1, because if a is equal to 1, there's no point, because 1 raised power anything is equal to 1, right? Then why? If a is equal to 1, like I said, then it means 1 raised power x is equal to 1. And that is true for every kind of x you can think of, because 1 over 1 raised power 1 billion is still 1 at the end of the day. So a has to be not equal to 1. So because if a is equal to 1, then 1 raised power x is 1 for all x. So equating exponents would be incorrect in that case. So a must not be 1. Then number two, if a is less than 0, we have this condition that a is greater than 0. If a is less than 0, meaning that a is negative, exponent rules may fail for non-integers. So we have these conditions. Identical bases, the base is greater than 0. That is, the base is positive and the base is not 1. Okay? So the base has to start from 2 in essence. So the general method for approaching that is what we've said already. To solve a raised power f of x equals a raised power g of x. Step 1, make the bases identical if it is not already identical. So you may have to rewrite if necessary. Then after that, you equate the exponents or the indices, and then you solve the resulting algebraic equation. So at that level, it now becomes like a regular polynomial equation, which we have already learned how to solve under the playlist I did on polynomial equations. And then we go to 5.4. Here we deal with some examples. We start dealing with examples already. So here we have linear in exponent problems. So linear in exponent problems. So at the exponent level, we can form a linear expression. For instance, you have 3 raised to power 2x equals 3 raised to power x plus 4 that we saw in the examples. So you can already see that the bases are identical, 3, right? So equate exponents, then that means you can see 2x is x plus 4. So you have 2x equals x plus 4. if you subtract x from both sides, you have 2x minus x equals 4. And that means x is equal to 4. And that is true because 2 times 4 is 8. So 3 on this, on the left hand side, you get 3 raised by 8. On the right hand side, you get 3 raised by 8 too, because 4 plus 4 is also 8. So you have linear expression in the exponent. So another example for linear expression in the exponent, you have this other one. Uh, you have 5 raised by 3 minus 5 raised by 3x minus 2 equals 5 raised by x plus 6. So you equate exponents again because the base is the same. So you have 3x minus 2 equals x plus 6, and then you subtract x from both sides. I mean, you transfer minus 2 to this side, add 2 to all the sides, you get 6 plus 2. Add subtract x from all the sides so that this x can go at back here. So you have 3x minus x equals 8, equals 6 plus 2. That means 2x is 8 and x is 4. So if you put 4 here now, 3 times 4 is 12. 12 minus 2 is 10. Then on this other side, 4 plus 6 is 10. So that is correct if you check it that way. So in some other cases, you may have to rewrite the exponents if they are not the same directly. You know, we are solving initial equations by equating, by comparing exponents, right? By comparing indices. Okay. So example 3 now, rewriting may be required in some cases. Here you have 9x equals 3x plus 2. So if you do all this, you end up getting x equals 2. I want to take it to the worksheet. That's why I'm not. So the answer is 2, as you can see already. So you have 9 raised by x equals 3 raised by x plus 2. Okay. So you have 9 raised to power x equals 3 raised to power x plus 2, right? That's what we have in this case. So what do we do? The bases are not the same, but it is easy to make 9 3 raised to power something. So 9 is 3 raised to power 2 clearly, but we have an x outside already, and we have 3 raised to power x plus 2. So of course, this one looks familiar. This is the power of power that we learned under the laws of indices. And if you have power of a power, you just multiply the powers. So this is equal to 3 raised to power 2x equals 3 raised to power x plus 2. And because the bases are the same, okay, you can just equate the powers. So that means 2x is equal to x plus 2. So if you subtract x from both sides, you have 2x minus x equals 2. So that means x itself is equal to 2. And that makes sense because you have, so if you come back here and check, you see that if you check, you have 9 raised to power 2, and that is 3 raised to power 2 plus 2. So this is 9 raised to power 2 equals 3 raised to power 4. 9 raised to power 2 is 81. 3 raised to power 4 is 81. So we are good to go. Okay. So you may have to rewrite the base if they are not the same. Then we move on to another uh, quadratic in exponent problems. That is, at the exponent level, you have quadratic expression. So you have 2 raised to power x squared equals 2 raised to power 5x. Again, the base is the same, so just equate the powers. So you have x squared equals 5x. So it's one mistake, it's very easy, right? To just divide through by x, right? Now you have x squared, you have x squared equals 5x. So you can make the mistake of dividing through by x and you have x is equal to 5. By doing this, the answer is correct, but you have lost one solution. So what do? You have x squared minus 5x equals 0. So this way, you won't have to lose any of the solutions. So be careful of canceling by what you're looking for. So here you can factorize x. So you have x into x minus 5 equals 0. And that means that x is equal to 0 or x is equal to 5. By canceling, by dividing through by x, you had lost the x equals 0 component of the solution. So this is x equals 0 or x equals 5 now. And of course, this was coming from which expression now? It was coming from 2 raised by x squared and 2 raised by 5x. So you can check. So you can always check to be sure if what you have done is correct. You have 2 raised by x squared, then 2 raised by 5x. So now, uh, for 0, at x equals 0, right? It means you have 2 raised by 0 squared, and this is 2 raised by 5 times 0. Of course, that means you have 2 raised by 0 equals 2 raised by 0. That's 1 equals 1, easy. Then on the other hand, you can check at x equals 5. So that means you have 2 raised by 5 squared equals 2 raised by 5 times 5. And they are basically the same. This is 2 raised power 25, and this is also 2 raised power 25. So correct. Okay. So that goes like that. So we have another example in that regard, and that this may be harder to check, but I mean, you already understand how it goes. So you have 3 raised power x squared minus 1 equals 3 raised power 3x plus 2. So equate the exponent because the bases are the same. So that means you have x squared minus 1 equals 3x plus 2. Then if you tidy things up, you have x squared. Okay, I guess I need to just do this on the worksheet. We already know the answer is 3 plus or minus root 21 over 2. So I want to go through the process. You have 3 raised power x squared minus 1, right? Um, so 3 raised power x squared minus 1 equals 3 raised power 2x plus 3. Is that correct though? 3 raised power x squared minus 1, then 3 raised power 3x plus 2, okay? 3 raised power 3x plus 2. 3 raised by 3x plus 2. So this is all we need to deal with because the base is the same. So we can equate the power. So we have x squared minus 1 equals 3x plus 2. So we try to tidy things up, make it a proper quadratic equation. You have x squared minus 3x. That's if this one comes from here. Then we then have minus 1, then minus 2 again equals 0. So that means we have x squared minus 3x minus 3 equals 0. So we have this. Then we can solve using a quadratic formula. So for the quadratic formula, we know x is equal to, of course, this is like ax squared minus ax squared plus bx plus c equals 0. So in essence, we are saying that uh, a is equal to 1. That's the coefficient of x squared here. So a is 1. Then b is the coefficient of x, which is minus 3. And c is constant, which is also minus 3. So based on that now, we can get x to be equal to minus b plus or minus square root of b squared minus 4ac all over 2a, like this. So that x now is equal to minus b is minus 3, right? So we have minus minus 3. So there was minus there before, so b itself is minus 3. So don't throw away the minus. So we have plus or minus square root of minus 3 squared minus 4 into a, which is 1, and c, which is minus 3. All of that all over 2 times 1, which is a, right? So we have x now to be 3, minus and minus is plus, plus or minus square root of minus 3 squared is 9, minus and minus is plus 12 here, all over 2. So then we have x is equal to 3 plus or minus square root of 21 all over 2. So here now we have, of course, if you want to split it up, you can say x1 is 3 minus root 21 all over 2, and x2 is 3 plus root 21 all over 2. So if you want to get it in decimal form, you can punch a calculator to get all this out, okay? So we have that. So that's why x is 3 plus or minus root 21 over 2. Then for example 6 now, we may need to rewrite the base because the bases are not clearly the same, but we can rewrite. So you have 4 raised to power x squared equals 2 raised to power 6x. So 2, you can easily rewrite, this is 2 already. You can write 2 as 4, 4 as 2. So you have, I mean, at the end of the day, the answer is x equals 0 and x equals 3. So I'll go again and do that. 4 raised power x squared, 2 raised power 6x, right? 4 raised power x squared 4 raised by x squared equals 2 raised by 6x. So now the bases are not the same, so we can't just compare the powers. But we know 4 is 2 raised by 2. Then x squared is out there, equals 2 raised by 6x. So now we have 2 raised by 2x squared equals 2 raised by 6x. So now the bases are the same, so you can compare the exponents or the indices. So 2x squared is equal to 6x. So you can be tempted to divide through by 2x, but don't resist the temptation. So you just have 2x squared minus 6x equals 0. Now you can factorize. 2 is common on the number part and x is common for the variable part. So you have x minus 3 now. So you have 2x into x minus 3 equals 0. So that means 2x is equal to 0, or x minus 3 equals 0. If you divide through, so you have here, of course, I think I'm just being finicky. Divide through by 2. So you have x is 0 over 2, or x is equal to 3. So that means x is equal to 0 and 3. So those are the values of x in that regard. Okay, so another thing is, what if you have different bases? Okay, I mean, we've been dealing with this all along. It's just another way to just talk about it. It's the same thing we've done. So if you talk about different bases, just like what we've done already, this is 8 raised power x plus 1 and 4 raised power 2x, right? So 8 is 2 raised power 3, 4 is 2 raised power 2. So if you bring it back, you have 2 raised power 3 to x plus 1 and 2 raised power 2 into 2x. So then you can say 3 multiplies x plus 1. So you have 2 raised power 3 times x plus 3 times. Don't make the mistake of just saying 3x plus 1. No, the 3 multiplies everything. Okay. Um, yeah, so you have 2 raised power 3x plus 3 equals 2 raised power 4x. And then you can equate the power, and now the base is the same. So you have 3x plus 3 equals 4x. That means if you, so 3 on one side, 3x, 4x minus 3x is x. So x is equal to 3 in that regard. So finally, we have a speech strategy for this, that if you see a raised power an expression and it is equal to a raised power another expression, maybe I should even make it better to say a raised power expression 1. Okay. I think I want to make this text also. Let's make this text. A raised power expression 1, okay, is equal to a raised power expression 2. Maybe another expression. So expression 2. So anytime you have this kind of thing, exactly. So a raised power expression 1 is equal to a raised power expression 2. Immediately ignore the base and equate the exponents and solve. Then always check the base conditions first. That's where you start from. Then common mistakes, forgetting to rewrite bases. So if the bases are not the same and you just equate, you're going to have a problem. Then equating exponents when bases are different. So if the bases are different, you cannot equate the exponent. Then forgetting quadratic equations give two solutions. Aha. So I think I said that a lot. That in a case like x squared equals 5x, you could easily divide through by x, and then you lose one solution automatically. So don't cancel out anything. So be sure that when you have a quadratic equation, that is the highest power is 2, you are going to get two solutions. Then ignoring base conditions. Don't forget the conditions for the base. That number one, the base must be the same on the left and right side. If they are not, you rewrite to make sure that happens. Once that is done, then make sure that the base is not negative, and also make sure that the base is not 1. So once those three conditions can be in place, then you're good to compare the exponents or the powers or the indices, if you like. Okay. So in summary, we see that if after equating, you get a linear equation, which is something like ax plus b equals cx plus d, just solve normally. If you get a quadratic equation, you have ax squared plus bx plus c equals 0. Factor or use quadratic formula. And then if you have different bases, you have to rewrite first, then equate, and then you can then solve like linear or quadratic equation, depending on whatever it turns out to be. So that takes us to our practice problems. As usual, we have 20 practice problems. I guess I can show 10 per in each case. So we have all these questions. I think I'll just pick one and solve it. One out of this 10, then one out of the next 10. Maybe I should pick number 10, which is 3 raised power x squared minus 4 equals 3 raised power 2x plus 5. Okay? 3, 3, 3 raised power x squared minus 4 equals 3 raised power 2x minus 5. Let me be sure of that. X squared minus 4, 2x plus 5. You see that x squared minus 4, 2x plus 5. Okay, 2x plus 5. Okay, the bases are the same already, so we can just equate the exponent. So x squared minus 4 equals 2x plus 5. Okay, so that means we have x squared minus 2x minus 4 minus 5. Okay, so x squared minus 2. So transfer this here, then transfer this also. So we have minus 4 minus 5, and all of that is equal to 0 since we've moved everything. So we have x squared minus 2x minus 9 equals 0. So I'll just go straight. Because I've done this before. So x here is just minus b. B here is minus 2. So minus minus 2 plus or minus square root of b squared, as minus 2 squared. Minus 4 into a. Coefficient of x squared here is 1. And c is minus 9. All of that over 2 times 1, which is a. So we have x to be 2 plus or minus square root of 4 plus 36 all over 2. Okay? So, and then that means x is equal to 2 plus or minus square root of 4 plus 36 is 40 all over 2. So one thing we can do here is, we can write 40 as, I think 4 times 10, right? 40 is 4 times 10. So we have a perfect square there. So 2. So in that case, now we have x is equal to 2 plus or minus square root of 4 is 2. Then root 10 all over 2. So we can divide through by 2. And then that means we have x equals 1 plus root 10. Sorry, 1 plus or minus root 10. That means we have two solutions. We can have x1 to be 1 minus root 10. And x2 can be 1 plus root 10. So that's what we get in that case. So for the next one too, maybe if I see another question, problem, I can also take care of that. And then, so that's from 1 to 10. From 11 to 20, which one should I go for? 11 to 20, 11 to 20, 11 to 20. Everything looks tempting. Um, I guess I want to go for 11 to 20. Mm, I don't know. Okay. Yeah, let me just leave everything. I mean they're pretty simple. So let me just try your hands on them and let me know how well they go. So with this, I come to the end of this interesting video on solving indicial equations, by equating indices. Okay. In the next video, we'll look at another method. They are all closely related, but except for maybe a few tweaks here and there, right? So let me know how helpful this is for you. And if there's something else you'd like me to try out, feel very free to let me know. If you have subscribed already, I thank you very much for doing that. If you haven't subscribed, why not do that right away? Go ahead, subscribe, hit the notification bell so you can always get alerted each time a new video is released. You can also become a member of this channel by clicking on join. That gives you special privileges like getting to see some videos before others, or being the only one to see some videos that others don't get to see if they are not members. And we can hang out online, physically, if you're in the same geographical location, to discuss anything that interests you on this channel. Ultimately, don't forget to comment, like, and share so that more people can have access to the great content I have going on here. Till I come your way again, keep doing maths right. Bye.